Very often in a C++ program, a class is defined and implemented by one programmer, whereas an application using the class is defined by a different programmer, or perhaps groups of programmers in both cases. So we have a separation in terms of skill level typically, and also responsibility, between class developers, who are usually experts, and application developers, who are hopefully also experts, but sometimes a little bit less expert than the class developers. Now, the class developer who wants to make a class available to some application developers to use needs to provide a header, usually named for the class with a .h file name extension, and that contains the class definition. By class definition, we mean this code consisting of the keyword class and the class name, followed by all of these components contained within curly braces, divided into a public section, which is usually member functions, and a private section, which is usually data members. In the examples that we've been looking at so far for this stock class, we've provided full definitions of each of these member functions. So we have our default constructor for the stock class with its member initialization list and body of code, although in this case the body is empty. Then we have our setPrice member function with its body of code that checks to make sure that the price is valid, and then either displays an error message or sets the price component of the stock to the value of P. And finally, our getPrice function that simply returns the value of that price variable. Application developers can only interact with this price either by calling setPrice to modify it or getPrice to find out its value. Any attempt to access price directly is going to fail because price is private. It turns out, by the way, that only truly trivial functions like getPrice that just return values of data members or similarly trivial things are actually defined in this so-called inline fashion within the class definition itself. That is, when we give the declaration of the function and its full implementation in curly braces inside of the class definition, this is referred to as an inline definition. And usually that's not done for functions that are other than trivial. There's two reasons for that. One is having all of the implementation details of all of the functions makes the class definition difficult for application developers to read. Secondly, there may be details about the implementation of some of these functions that you would like to keep secret from your users, particularly if you are developing a library of code that you're selling to some other customers. Okay, so the class developer has to provide the header containing the definition, and then, because often a lot of the functions will be defined in separate pre-compiled object code files, the class developer will have to provide a library of this pre-compiled code as well. Let's see how we would take this stock class and an application using the stock class and split this up into three separate files, which would be a more conventional way of implementing and using a class. Okay, so here on 19 and 20 are the definition of the stock class stored in the stock.h header file, and the implementation of member functions stored in the stock.cpp code file. Now there's an illustration on slide 18 that I have decided to skip over, and I'll come back to that in a little bit. So the header file is what application developers are able to see. And this header tells someone who wants to use this class that the name of the class is stock, and that it has three public member functions, namely a default constructor, a function called setPrice that expects to receive a double as its argument and that returns void, and finally a function called getPrice that takes no argument and returns a double. And in this case, we have a full inline definition of the getPrice function, because all it does is to return the value of the price variable. Now, the current price of the stock is maintained within this price variable, which is a double, but it's private, so although the application developer can see that it's there, the application developer is prevented from accessing that price data member directly. Okay, so of the three member functions defined in the public section of this class, one has its definition defined in line. The other two only have declarations in the header. The definitions of those things have to go in the code file associated with this header file. Now, notice in the code file that we start out with our inclusive IO stream and using namespace standard as usual. We also have to include the stock header, which will pull in a copy of the contents of the stock.h file, so that for the remainder of the file we know exactly what a stock class consists of. In here we're going to define the default constructor, and we're going to define the setPrice function. Now, because these two function definitions are not directly contained within the class definition itself, I need some way of telling the compiler that these two function definitions belong to the stock class. And that's what this double colon notation is about. Stock : means that this function is a member of the stock class. In fact, it's better to read this from right to left, as I have done with references and with pointers, and to say stock is a member of the stock class. Likewise, setPrice is a member of the stock class. Notice that the return type for setPrice is in front of all of that. So for our constructor, let me erase some of this yellow. So for the constructor, this is the default constructor for the stock class, and it is a member of the stock class. It is not some other function named stock unassociated with this stock class. Similarly here, setPrice is a member of the stock class. It is a function that takes a double and returns nothing. Now, to complete the implementation details for the default constructor and for the setPrice function, in the case of the constructor, we have our member initialization list that sets the data member price to 1.0, and then we do whatever else is necessary to initialize a stock object. Well, there's nothing else that needs to be done. So we do have to have a body of code, but the body is empty in this case. And then for setPrice, we also have our implementation details in the body of code, and we've added a little additional bit of code here. If the current price of the stock is 0, then this company is bankrupt, and we're not going to magically allow this company to come back to life by having a positive price. All right, so if the price is 0 now for the stock, we're not going to do anything. Otherwise, we're going to test whether the price requested is greater than or equal to 0, and if so, set the price to that value P. Or, if the requested price is less than 0, we're going to display our error message. So in summary, the header defines the stock class, including its publicly accessible behaviors and its private state information. The code file associated with that class completes the definitions for any member functions that were only declared but not fully defined within the stock class definition. Continuing on, we have an application program here on slide 21 that's making use of this stock class. The application program also has to include the header so that within the application we'll know exactly what the interface to a stock is. And in the application, which is just contained in this short little main function, we're declaring a stock object, so that's going to create a stock object named XYZ on the stack. By default, that stock will end up with a price of 1.0. We're going to get the price, which simply returns the value of the price variable. At this point, that will display as 1. Then we're going to set the price to 47.12. And then we'll get the price again to see that that was properly set. All right, well now let me back up to the diagram that I skipped over to see how these three different files are related together in terms of what your compiler does. So we have three separate source code files. And these icons here are my pitiful attempts to represent these three files. The stock header defines the stock class, including its behaviors and its state. That is, including its public member functions and its private data. Now, that stock header is included using an include directive within the application source code file and also within the stock.cpp implementation file. When you compile your program, that include directive is handled by a phase of the compiler called the preprocessor. And literally all that happens as a consequence of that include directive in each of these two .cpp files is that a full copy of stock.h gets sucked in place of the include line. Now, once that include directive has been processed, the compiler then converts the resulting code into binary executable code. And that happens for both the application file. In a Linux environment, we're going to end up getting a binary file called myapp.o. And it also happens for the class implementation code file, from which in Linux we're going to get a stock.o. Now in Windows you would get a myapp.obj and a stock.obj. They're both compiled, not human readable object code files. And then finally, the final step that the compiler performs is what's called linking. And the object code for the application, together with the object code for the stock class, and any facilities from the standard library that the program uses, such as the cout standard output stream object, all of those things are linked together to create a single executable program file. And I have inconsistently shown the Windows name for that program file, myapp.exe. On Linux, it would actually just be called myapp. Okay, so that is the process by which these three separate source code files get turned into a single executable program file. All right, so now let's continue making enhancements to our stock class. It doesn't really make sense for a stock to have an initial value of 1 by default. When a stock is listed, it has some price established. So let's move the default constructor into the private section down here to prevent default construction from happening at all. And instead of the default constructor, let's have an overloaded constructor that is another function whose name is stock, the same as the name of the class. But this overloaded constructor is going to take a double as its argument, and that will be the initial stock price. Now, because for the stock class we have made the default constructor private, it's not going to be possible in an application to declare stock objects without specifying a price. The only public constructor is this one that does require a price to be specified as an argument. We did not provide an inline definition of this constructor in our header file, so let's take a look at its definition in our code file. By the way, we've named this header as stock2.h and this updated code file as stock2.cpp. We're including stock2.h at the top of this code file. Here is our overloaded stock constructor. This is a function named stock that is a member of the stock class. All right, so since the name is the same as the name of the class, it is a constructor. It requires a single double parameter, which will be the initial price. Now, we're using our member initialization list to initialize the value of the price data member. However, there is a possibility that the init price argument is bogus. So we're using our good old question colon ternary operator here in the initialization list to check is the initialization price that was passed in greater than 1? If so, we will use the init price that was passed in. Otherwise, because we can't list a stock that's less than $1, we're going to use $1 as the initial price. And there's nothing else to do once we have defined the initial value of the price member. We also have our setPrice member function defined in here. Since we have declared the stock default constructor to be private, it turns out that we don't any longer even have to define that function. That function cannot be called from an application anyway, so it turns out we don't even need to provide a definition for it. Here on slide 24 is our updated application program. If we were to attempt to say that XYZ is a stock object with default initial value, we would get yelled at by the compiler because there is no default constructor available any longer. We do have to specify an initial value for the stock when we declare the stock object. And since 44.0 is greater than 1, we will have 44.0 as our initial stock price. And the remainder of the program works as before. Now in C++ 11, it was decided that rather than having the default constructor declared private, an alternative way of specifying that that constructor is not permitted is to use the notation equals delete. So you can still have the default constructor declared in the public section, but its definition is equal delete, which means that you can't call it. Okay, so the stock class that we have used here to illustrate the idea of public member functions and private data members and constructors and functions that set values and get values and so on is incredibly simple. We only have one data member. We're not doing any dynamic memory allocation. We're not accessing any remote network resources, or we're not accessing a file on disk. Consequently, for this class, we have the same kinds of operations available to us that we get for free if we had just declared this thing as a struct. That is, assignment is defined for us, passing a stock into a function by value, or returning a stock as a result from a function, initializing a new stock as a copy of another stock. All of this stuff is available to us for free. If we do assignment, or if we do argument passing, or if we do initialize a new stock object from an existing stock object, all that happens is that the data members are copied from the existing stock into the other stock. So because we get these kinds of behaviors for free, we can go ahead and define functions that are not members of the class, but that use stock objects. Here we have a function named highest price. We're passing in two stock objects by value. Internally within this function, we're using the parameter names S1 and S2. We're using getPrice in each of those, and if the price of the left-hand stock is greater than the price of the right-hand stock, we're returning a copy of the left-hand stock. Otherwise, we're returning a copy of the right-hand stock. And here on slide 28, we have an application, a main function, that's using some of these services we get for free. Now, we're still not going to be able to create a default stock because default construction has been deleted. We are going to be able to declare a stock object with an initial value as long as it's greater than 1. And for free, we're going to be able to create a stock object that's simply a copy of another stock object. So DEF here is initialized from XYZ by simply having XYZ's price data member copied into DEF's price data member. Next, I'm creating a stock object named JKL, initialized with 47.5 as the price. And I get assignment for free. That is, I can say XYZ gets JKL. That has the effect of copying JKL's price value, 47.5, into XYZ's price. And finally, I'm using the highest price function that we defined on slide 27 To compare the prices of X, Y, Z, and DEF, a copy of one of those will be returned, and then that value returned gets assigned into JKL. Okay, so for extremely simple classes, getting all of this stuff for free might be a nice feature. However, for our binary tree class, this kind of copying that we get for free of just copying the data members of one object into the corresponding data members of another object absolutely will not work. We are using a pointer called top to keep track of where the first node is at the top of our binary tree. And if we use the free copying that we get to assign, let's say, one binary tree to another, all that would end up getting copied is the value of the top pointer, not all of the nodes within the tree. So we would end up, in this default case, having two binary tree objects whose top pointers point to the same tree. And so, among other catastrophes that would occur, when we're done using one tree or the other, and we delete that tree, and then later on we try to use the other tree, well, that other tree no longer actually exists because it was really just the same tree as the one that we deleted. Okay, so we cannot rely on default copying. What we have to do is to define all of these operations ourselves. That is, we must define a default constructor. We also need to define a copy constructor that knows how to properly copy an existing binary tree into a newly declared binary tree. And we're going to have to define our own assignment operator that knows how to assign a correctly structured copy of all of the nodes in one tree into another tree. Finally, as a way of making our binary tree very easy for application developers to use, we're going to define a destructor that knows how to properly deallocate all of the nodes in a tree and set its top pointer to 0 when we're done using that tree. That is, the destructor is like the inverse of the constructors, and it needs to undo all of the memory allocation that the constructors did. As a reminder, here on slide 30, we have an example of a binary tree with its top header node pointing to the topmost node among the 6 nodes in the tree. If we create a class for our binary trees, then top will be a data member within a particular binary tree object. So here I have an object tree1 whose data type is binary tree, and internally one of its data members is top, the header node pointing to the topmost of the BT nodes allocated in the heap. What I do not want to have happen by default is when I create a new binary tree as a copy of an existing tree. Here I have a binary tree tree2, which is a copy of the tree tree1. I do not want merely to copy the pointer so that now I have two different objects referring to the same memory. What I do want to have happen, and what I need my copy constructor and my assignment operator to do, is to allocate within the heap a completely independent copy of all of the nodes from tree 1 and have tree 2's top header node point to the topmost node of that copy. Okay, so starting on slide 31 and continuing through slide 35, in this case we're going to be developing a single source code file that defines a binary tree class, implements the binary tree member functions, and then at the bottom we have a main function that exercises the binary tree by creating one and calling some functions. Now let me display slide 32 as well. Alright, so here's the top of our file on slide 31. We are including IOStream and specifying using namespace standard as usual. In the binary tree class, we have several public member function declarations, and we only need one private data member to keep track of the state of the binary tree. As the private data member, we're using top, whose data type is pointer to BT node. Now, the BT node structure is going to be as it was before, with a value, a left child, and a right child. And we'll come to its full definition later. However, it's likely, once we have gotten this binary tree code fully developed and tested, we're going to want to split this up into a header that just defines the class, a code file that implements the member functions, and then have separate application files that make use of the binary tree class. So to hide unnecessary detail from a user of a binary tree class, all we're going to tell the compiler at this point, and therefore the user at this point, about BT node is that BT node is a structure. All right, so this thing here is called a forward declaration. We're informing the compiler, hey compiler, BT node is a structure. Therefore, the compiler will be happy with me saying that top is a pointer to a BT node. Later on, when I need to actually implement code involving using top, I will have to tell the compiler the details of what a struct BT node contains. But the forward declaration is all I need in order to be able to tell the compiler that the top data member is a pointer to some kind of struct. All right, so in the public section, we have a default constructor being declared. That's the constructor that's going to be invoked if I declare in an application a binary tree object and I don't specify any initialization information. I also have a copy constructor. This is the constructor that gets called if I declare a binary tree object and I initialize it with a copy of some other binary tree object. Actually, let me back up a few slides to our little example stock application. Okay, so back on slide 28, for the stock class, we disallowed default construction, but for the binary tree, it makes sense to allow default construction. It's perfectly reasonable to have a binary tree object introduced into our application that's initially empty. So we're going to allow default construction. This statement here is an instance of copy construction. We are creating a new stock object DEF, and we've indicated that we want DEF to be a copy of XYZ. We similarly want to be able to say things like binary tree, tree2, is initially a copy of tree1. And that is the situation that this copy constructor is designed to handle. Notice that the argument being passed in to the binary tree copy constructor is a reference to a binary tree const. That is, we pass in a reference to an existing binary tree. We specify that it's const because our constructor is promising that it won't change that existing binary tree. And we're passing in a reference for efficiency here. Now, on slide 28, we also have an example of assignment where XYZ is a stock object, JKL is a stock object, and we're saying XYZ gets JKL. We do want to be able to do that with binary trees. We want to be able to say tree1 gets tree2. To accomplish that, we need to define what's called an overloaded assignment operator. Okay, we want to be able to use the equal sign to do assignment. That is actually going to invoke a member function, and the name of a function that specifies how some operator symbol, like the single equal sign, is implemented, is given this special name, operator equal. If it made sense to define how multiplication works for binary trees, then we would have a function whose name was operator star. All right, so we are going to define operator single equal sign so that we can control exactly what assignment does, and we don't simply end up with the left-hand binary tree object's top simply being a copy of the right-hand binary tree object's top. All right, now the fourth member function being declared here is what's called the destructor for the class. It has this funny name tilde binary tree because the tilde symbol applied to a pattern of bits That is, the tilde symbol typically applied to an unsigned integer value inverts all of the bits so that all of the 1 bits become zeros and all of the 0 bits become 1. So when Strustrip designed the class interface, he decided, okay, well, destruction is the inverse of construction, and so we'll use this name tilde class name as the destructor for the class. A given class may have many constructors, but is only permitted to have one destructor. Okay, so we have our default constructor, our copy constructor, our overloaded assignment operator, and our destructor. Then we're going to have other member functions that do things that we've already implemented for our original binary tree code, including we want to be able to insert an integer value into our binary tree. We want to be able to put the binary tree to the cout, standard output stream object. We want to find out the minimum value stored in the binary tree. We want to be able to find out the size, that is the number of items within the binary tree, and so on. We can easily imagine other methods or member functions that we would like to be able to have our binary tree objects support. All right, so now that we have defined our binary tree class on slides 31 and 32 with several public member functions and one private data member, below that, starting on slide 33, we finally reveal to the compiler what a BT node struct actually looks like. This is familiar from before. We have an int value member and left and right subtrees, that is pointer to BT node members. And we're ready to start defining these member functions that were declared in the binary tree class. So first of all, let's define the default constructor. Well, the default constructor is easy. We know that to represent an empty binary tree object, we simply want the top to be set to null pointer or 0. So this one-line definition here says that binary tree is a member of the binary tree class. Okay? It takes no arguments, so this is the default constructor. And the definition consists of the member initializer list, in which we're saying top is initially null pointer. The body of code has nothing remaining to do, so the body of code is required, but it's empty. Now, in real life, just so you know, I would define this on 3 lines in my code file. I would have the binary tree : binary tree parentheses on a line, and then below that I would say : top null pointer, and then below that I would have my empty body of code. I've got it squeezed onto one line here simply because I'm running out of space on slide 33. Continuing on, here is our destructor. This is our binary tree destructor. It is also a member of the binary tree class. And we already have this function that we developed before called binary tree delete that we can simply use. So we're going to call binary tree delete, which requires us to pass in the address of the header node, that is the address of top. And we know that binary tree delete will do the correct thing. All of the nodes in the binary tree will be deallocated, and top will be reset to 0 or null pointer. Next up, we have the insert function. Okay, insert is a member of the binary tree class. It is a function that takes an int and that eventually returns void. We can simply call the binary tree insert function that we already have. We know that that's going to change the shape of the tree, so we pass in the address of the header node. In particular, of course, if the tree is empty, then top itself will be 0, and so we have to pass in the address of top to replace the value of top with the address of the first newly allocated node. The second argument, of course, is the value that we want to insert. Then, continuing on, here's what our application can look like. once we have defined the default constructor and the insert member function, as well as the destructor. Okay, so this code in main says tree1 is a binary tree object. Initially it's empty. Into tree1 I'm going to insert a 12, then insert a 7, then a 9, 13, minus 4, 29. So that will build in memory the binary tree linked data structure that we saw on slide 30. When we call tree1.put, I didn't show the implementation of that, but all that function is going to do is to call put binary tree with top passed in as an argument. So a representation of the binary tree is going to be displayed on the screen. Now the cool thing about the destructor is you don't have to invoke it explicitly. In fact, you don't invoke it explicitly. When we reach the end of the scope for this local variable tree1, it turns out that the destructor for tree1 will automatically be called so that we can be assured that all of the memory that was allocated by all the insertions that we did into tree1, all of that stuff is properly deleted without us having to do anything special. Okay, so we still have more functions to look at, but we have implemented and used the default constructor, the destructor, the insert function, and we've used the put function without me showing you that all that function does is to call put binary tree. Now compare the simplicity of the binary tree class application on the left-hand slide, on slide 35, with our original collection of interface functions involving pointers to btnode. Declaring and using binary tree objects in applications is much, much easier for the application developer than having to declare top as a pointer to a btnode initialized with 0, then remembering to pass in the address of top as well as values to this nasty long function binary tree insert, not passing in the address for put binary tree, and having to remember to call binary tree delete, again with the address of top. So there's a lot more notation, a lot more machinery, a lot more things to remember in our original binary tree code involving this structure and all of these interface functions. With our binary tree class, in contrast, there are no pointers, there are no addresses to take, there are no long function names that you have to remember and call. There's no need to delete the tree, that just happens for you automatically, and everything is much cleaner and simpler. Now, we are also going to want to be able to make a copy of an existing tree into a new tree. This is going to call our copy constructor here. Tree2 is a binary tree object initialized as a copy of tree1. And we're going to want to be able to assign one tree to another. Furthermore, we want assignment to associate from right to left and to return a value so that a statement like tree1 gets tree2 gets tree3 makes sense. Of course, this should be evaluated as tree3 being assigned into tree2 and then tree2 being assigned into tree1. So this is going to require us to define the copy constructor and the overloaded assignment operator. That's what we're going to take a look at next. Whether we're invoking the copy constructor or the assignment operator, each of these is going to require us to make a copy of some existing binary tree. And to handle the low-level details of that, down at our pointer to BT node level with these left and right children and so forth, we're going to define this function make binary tree copy. And here it is. It's relatively straightforward, at least so long as you have a good handle on recursion. So we get passed in the header node for an existing tree. That comes in as a pointer to a BT node const. That means make binary tree copy promises it will not change the argument tree. When make binary tree copy is done, it returns a pointer to a BT node, which is the topmost node of a new copy of the original binary tree? Well, copying an empty binary tree is super easy. If the existing binary tree is empty, that is, if top is 0, all we have to do is to return a null pointer, or 0, and we're done. On the other hand, if top is not 0, that means that there's at least one value in the binary tree. So we will simply create a new binary tree node with the existing tree's topmost value as its value, and then the left and right subtrees of the new tree are simply copies of the left and right subtrees of the existing tree. This should look very familiar. It's essentially the same as the recursive implementation of mint copy c list, except that instead of recursively copying one list, we're recursively copying two subtrees. And now that we have this low-level mic binary tree copy function available to us, implementing the copy constructor is quite trivial, really. Here is the interface for our copy constructor. It's a constructor that takes a reference to a binary tree const as its argument. Here's the implementation on slide 39. Binary tree is a function that is a member of the binary tree class. We're calling the parameter other, so we're copying a new tree from some other already existing tree. And all that's involved is to call mic binary tree copy on the argument tree's top and use the return value of that, which is a pointer to the topmost node, as the initial value for the new tree's top. The body of code is required, but has nothing remaining to do. Okay, so that takes care of the copy constructor. And so now we've implemented the default constructor, the copy constructor, and the destructor. The last one of these four member functions that we absolutely have to define ourselves is the overloaded assignment operator. In the overloaded assignment operator, notice that the argument is a reference to a binary tree const. That will be the binary tree that's on the right side of the assignment operator, the right side of the single equal sign. The current binary tree object is the one that's on the left side, and it's the one for which this overloaded operator function is going to be called. Now, because of the way assignment is expected to work, when this function is done, it needs to return a reference to the current binary tree object so that the current binary tree object can then be used in another assignment to another binary tree on its left, for example. So let's see how we put together this assignment operator. First of all, we need to introduce another keyword, which is this. Within any member function for a class, the keyword this is automatically set up, and it points to the current object. It serves the same purpose as self in Python. However, in Python, self is a reference, whereas in C++, this is a pointer. Also, in Python, anytime you access a member of a class, whether that's data within the object or a method within the object, you always have to put self in front. So you say self.rate, self.name, self.size, and so forth. In C++, in most contexts, this is optional, although it's going to turn out in our assignment operator definition that we have to use this because we are returning a reference to the current binary tree. All right, so regardless of class, let's suppose that we've created a class called Zebra, and we are now executing some member function that's defined for the Zebra class. Internally within that member function, anytime I use this, it's understood to be a pointer to Zebra, and particularly a pointer to the current Zebra object. In order to work in the way that a user expects, assignment must return a reference to the current object. And in particular, since this is a pointer to the current object, star this is the current object, and therefore return of star this is what the assignment operator function must return. Now also for clarity, if you have a member function that's manipulating two binary tree objects or two zebra objects or two employee objects or whatever, it's generally good practice to access members of the current object using this, and to access members of the other object using a parameter name such as other. So we would have, for example, this arrow top as the top member of the current object versus other dot top as the top member of the other object. All right, so here's our actual implementation on slide 41. There are 4 steps in this implementation, and if you always follow these 4 steps, you should have good success overloading the assignment operator for any class that you create. The first step is to make sure that you are not attempting to assign an object to itself. For example, if you have a binary tree object named tree1, you should check to make sure that you're not saying something like tree1 gets tree1. The way to do this is to compare the keyword this with the address of other. Other is the reference to the right-hand side binary tree of the assignment, and if this, which is the address of the current binary tree, is the same as the address of the other binary tree, that means you are attempting to assign one binary tree to itself. In that case, it's legal, you don't have to complain, but there also isn't really anything to do. So simply return star this and you're done. All right, so that's step 1. Assigning an object to itself doesn't involve any work, just return star this. And notice, as we talked about when we looked at the declaration, that we're returning star this, that is, we're returning the current object by reference. All right, so once we've dealt with self-assignment, the second step is to always clean up any data associated with the current object. For example, in the case of the binary tree, since we're assigning some other binary tree to our current binary tree, that means we had better delete all of the dynamically allocated nodes that already exist for the current tree. We can get away with just saying delete ampersand top, because top is understood to belong to the current binary tree. But for clarity, since we also have some other binary tree floating around, it's common to use this arrow top rather than just plain top. Recall that this arrow top is equivalent to star this in parentheses dot top. So once we've completed step 2, and we have cleaned up or gotten rid of any data in the current object, in step 3, we then update the current object with a copy of all of the necessary data from the other object. In our case here, this simply involves calling McBinary tree copy on the other tree's top, that is on the right-hand tree's top, and assigning the address that we get back to this arrow top. Again, in this context, the this arrow is optional and we could leave it out. All right, so following that third step, which is copying the data, our final step is to return star this, that is, return a reference to the current object, and we're done. Okay, so here on slide 42, we have a main function, an application, that is declaring and using 3 binary tree objects. The first one, tree1, is a binary tree that's going to be created by the default constructor, and all the default constructor is going to do is to set the top data member within tree1 to 0, or null pointer. The second binary tree object, tree2, is going to be initialized using the copy constructor. It will be a copy of tree1. That's actually not very interesting because tree1 doesn't have anything in it. But even if tree 1 did have stuff in it, this would be a successful copy of all of the data in tree 1 into tree 2. We're then creating tree 3 as a binary tree object using the default constructor. And into tree 3, we're going to insert two values, 888 and minus 888. So at this point, tree 1 is empty, tree 2 is also empty, tree 3 has two nodes in it. And now we're going to use our overloaded assignment operator. We're saying tree 1 gets tree 2 gets tree 3. This is evaluated from right to left, so if we explicitly put in the implied parentheses, what's going to happen here is that L tree 2 gets L tree 3 first, and then the result of that, which is L tree 2, is assigned to L tree 1. These usages of the assignment operator in the statement involving a couple of assignments gets converted into function calls of the operator equals function that we've defined in our class. These function calls are nested from right to left because this operator associates from right to left. So we first execute L tree 2 dot operator gets L tree 3. That is, within the body of this operator gets function, L tree 3 is the other tree, L tree 2 is the current tree object. This is pointing to L tree 2, and other is a reference to L tree 3. All right, so we first test whether this is equal to the address of other, that is, whether the address of L tree 2 is equal to the address of L tree 3. That's not the case. L tree 2 and L tree 3 are different objects. So we then come down and we delete all of the data associated with L tree 2. Actually, that delete function does not do anything because top is null. Okay, but if there had been information in L tree 2, we would have deleted all of that. Then we make a copy of L tree 3 using make binary tree copy of L tree 3 dot top, if you will. Other is a reference to L tree 3. L tree 3 does contain two values, 888 and minus 888. So we get a copy of that two-node tree, and L tree 2 now has its top variable updated to point to the topmost node of that copy. Finally, we return star this. That is, we return L tree 2 by reference. Therefore, the return that we get from all of this green code here is a reference to L tree 2, which can then immediately be passed down to the overloaded assignment operator being invoked for L tree 1. Okay, so in the red statement here, we have L tree 2 being passed in by reference, so L tree 2 is other, and L tree 1 is the current binary tree object, and the whole thing happens again. So when we're done with that statement, we now have L tree 1, L tree 2, and L tree 3, each having its own independent copy of this two-node tree with 888 at the root and minus 888 as the left subtree. When we hit the closing curly brace at the bottom of our application, then the destructor gets invoked in reverse order for each of these constructed trees. That is, the destructor gets invoked for tree 3 first, then for tree 2, and finally for tree 1. And then the program is done. All right, so back in lecture 13, we introduced a struct representing a BT node in a binary tree, and using dynamic allocation with pointers to these allocated BT node structures, we were able to put together a collection of interface functions that enabled us to create and manage binary trees. And we complained about a variety of aspects of that approach. With the binary tree class, we've now fixed most of these problems. We do now have automatic initialization using constructors, the syntax is a lot less messy because the application programmers, for the most part, don't have to worry about pointers and addresses and so on. The function names are nice and brief. We have insert and put and size and so forth, rather than these long interface function names. It's much harder for the user to wreck the tree intentionally or by accident because the top data member is private within each object. We've added an assignment operator, and following a similar process, we can also add a quality test, a put-to operator for displaying a binary tree to see out, and other such operators as make sense. And because the user is only going to be able to see the class definition with no details about how the member functions are implemented and no details about what a BT node actually is, users are not easily going to be able to write code that makes assumptions about the implementation. We're still restricted with this class to a binary tree of int values. For a binary tree of char values or double values, we'll also need to know about templates, which we'll discuss briefly later. Before we wrap up Lecture 15, I want to return again to slide 31 and emphasize the importance of these four member functions that we defined here: the default constructor, the copy constructor, the assignment operator, and the destructor. Now, in the case of the default constructor, copy constructor, and assignment operator, if you do not define these things yourself, the compiler will do some default behavior for you that is very likely not what you're going to want. So, for any class that you define, class X in this case, you're going to want to have a default constructor, a copy constructor, and an overloaded assignment operator for that class. And the interfaces need to look like is shown on slide 31 and also in this abbreviated version in my Ubuntu window on the right-hand side. That is, the default constructor takes no argument. The copy constructor takes one argument, which has to be a reference to an X const, if your class is X, or a reference to a binary tree const in the case of binary tree. The overloaded assignment operator has to take one argument, which is also a reference to an X const, or a reference to a binary tree const, or whatever your class is. And it also must return a reference to an X, a reference to a binary tree. So in addition to defining those three things to make sure that the compiler doesn't do something bizarre for you, you also should always get in the habit of defining a destructor for your class. It's possible, if your class is not doing any dynamic memory allocation, or if your class is not opening any files, or not opening any web access, or things of that kind, that there won't actually be anything necessary for the destructor to do. But it's still good discipline to define a destructor for any class that you create, even if the body of the destructor is empty. Okay, and so with that final bit of advice, we are done with Lecture 15.